Somewhere far beyond the planets, far beyond the warm circle of light we call home, two small machines are still moving outward through the dark. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. They are not large. Each one is about the size of a small car, wrapped in foil and metal with a long arm holding instruments and a wide dish pointed back towards the sun. They were built by human hands more than 40 years ago, and they have been falling away from us ever since. If you could rise above the Earth tonight and look outward, past the moon, past the orbit of Mars, past the great striped clouds of Jupiter and the pale gold rings of Saturn, you would still need to keep going, past Uranus, past Neptune, past the slow icy belt of small worlds that drift beyond the last planet, out into the wide, cold dark where the sun is only one bright star among many. That is where Voyager 1 and Voyager 2 are now. They are the farthest human-made objects that have ever existed. The scale of where they have gone is hard to picture. Light, the fastest thing in the universe, takes about 8 minutes to travel from the sun to the Earth. From the sun to Voyager 1, light needs more than 22 hours. A radio signal sent from one of these probes, traveling at the speed of light, spends almost a full day crossing the gulf before it whispers into our antennas. And then we send a message back, and that message takes another full day to reach the probe. A simple hello and a simple reply can stretch across 2 days of silence. They have been moving for so long that the people who designed them have grown old, and some have passed away. The engineers who first listened to their signals in the late 1970s are not the engineers who listen now. The computers on board are older than most of the people working with them, and yet somehow both probes are still sending faint, patient signals, smaller than the energy of a refrigerator light, are still arriving at Earth from a place no human will likely ever visit. This is the quiet mystery at the heart of tonight's episode. Two small machines drifting at tens of thousands of miles per hour in opposite directions through a region of space we still do not fully understand. We know roughly where they are. We know roughly what they are passing through. But the edge of the sun's influence is a strange, soft boundary, and the space beyond it is not empty in the way we once imagined. There are particles out there, and magnetic fields, and slow currents of matter blown from other stars. The Voyagers are sailing through that unfamiliar sea, and they are sending back data that researchers are still trying to make sense of. There are questions about how long they will keep talking to us. There are questions about exactly where the solar system ends and where true interstellar space begins. There are questions about what the probes might drift near in the deep future, thousands and millions of years from now, after their power has long since faded and they have become silent travelers, carrying only a thin gold record and the memory of a small blue world. For tonight, we are going to sit with all of that. We will follow the Voyagers from their summer launches, through the giant planets, past the rings and the strange moons, out to the edge of the heliosphere, the great bubble of solar wind that surrounds our sun, and then beyond into the place where no spacecraft has gone before. We will listen for the soft signal that still arrives, one faint whisper at a time, and we will sit with the open questions that no one has yet answered. You do not need to remember any of this. There is no test. There is no urgency. The Voyagers have all the time in the world, and they will keep drifting whether we are awake or asleep. So let the room soften around you. Let your breath slow. Let your shoulders rest. Imagine for a moment that you are looking up into a vast, quiet dark, and somewhere out there, far beyond anything you can see, two small machines are still moving, still listening, still sending. They have been doing this for a very long time, and the story of what they have found and what they have not yet found is where we will spend the next few hours together. To understand the long silence between us and these two small machines, it helps to begin at the beginning, to picture the warm late summer of 1977, to picture two spacecraft, each smaller than a small car, sitting quietly inside the tops of two rockets in Florida. They weighed about 825 kilograms each at launch, which is roughly the weight of a grand piano. They were not large, they were not heavy. They were built with the careful, slow work of human hands, and they were about to leave the Earth and never come back. Voyager 2 launched first on the 20th of August, 1977. Voyager 1 launched second on the 5th of September of that same year. The numbering can seem strange. The reason is simple. Voyager 1 took a faster, shorter path and overtook its twin within a few months. So the second to launch became the first to arrive. Each probe carries a body shaped a little like a squat, 10-sided drum. From that body, long arms reach outward into the dark. One arm holds a science boom lined with instruments meant to taste the thin gas and faint magnetism of space. Another arm holds two small generators packed with a slowly decaying lump of plutonium. And rising above everything is the dish. A great round antenna, 3.5 meters across, always angled patiently back toward home. That dish is about the width of a small bedroom. It is how the probes speak to us. It is how, even now, they whisper across the dark in a voice quieter than a single watt of household power. To picture how faint that signal is, by the time it reaches Earth, imagine the warmth of a refrigerator light bulb shining toward you from billions of kilometers away. The number is so small that words almost lose their grip on it. Each Voyager carries a set of cameras, a magnetometer to feel magnetic fields, instruments to count tiny charged particles, and detectors for the radio hiss of distant plasma. Some of these instruments have gone quiet over the years. Some are still awake. The ones still awake send their thin trickle of data back across a gulf so wide it takes light itself many hours to cross it. To make that gulf feel real, try this. Light from the sun reaches the Earth in about 8 minutes. Light from the sun reaches Pluto in about 5.5 hours. A radio signal from Voyager 1 now takes more than 22 hours to reach us, traveling the whole time at the speed of light. The signal you might hear tonight, if you could hear it, left the spacecraft more than a day ago. Voyager 1 is the most distant human-made object in existence. As of the mid-2020s, it sits more than 24 billion kilometers from the Sun. Voyager 2 is a little closer, but still more than 20 billion kilometers out. To put those numbers in something the body can feel, the Sun is about 150 million kilometers from Earth. So Voyager 1 is now more than 160 times farther from the Sun than we are. The probe moves outward at roughly 17 kilometers every second, which is fast enough to cross the continental United States in under 5 minutes. And yet, even at that speed, the stars are still impossibly far. If Voyager 1 were aimed straight at the nearest star system, which it is not, it would still take tens of thousands of years to arrive. Space is mostly emptiness, and the Voyagers are mostly traveling through nothing at all. They are made of aluminum and gold-plated copper, of titanium fittings and ceramic insulators, of carefully folded wires and small sturdy computers with less memory than a modern car key. Their brains were designed in the early 1970s. The code that runs them was written by engineers, many of whom have since retired or passed on. New engineers now study that old code like a language, learning to speak with two machines older than most of the people listening to this story. Their power comes from the slow decay of plutonium-238, which gives off heat that the generators turn into electricity. That heat is fading, a little less each year, a little less each month. The probes have a fixed amount of warmth still to give, and when it runs out, the radios will go silent. How long that takes, and what they might still teach us before it happens, is part of the open question this episode rests on. For now, picture them. Two small drums of metal and gold, drifting slowly outward, dishes turned forever toward a pale blue point of light far behind them. The story of the Voyager probes does not really begin in the summer of 1977. It begins years earlier, in the quiet calculations of a young researcher who noticed something strange about the outer planets. In the mid-1960s, a graduate student named Gary Flandreau was working at the Jet Propulsion Laboratory in California. He was studying the positions of Jupiter, Saturn, Uranus, and Neptune, and he saw something that almost no one else had thought to look for. The four giant planets were slowly drifting into a rare arrangement. Once every 176 years or so, they line up in a wide curving pattern across the sky. A single spacecraft, launched at just the right moment, could swing past all four. Each planet's gravity would bend the craft's path and fling it onward to the next. No fuel needed for the long jumps, just the gentle pull of giant worlds, handing the traveller along like a small stone passed from hand to hand. This idea was called a gravity assist. The next chance to use it on all four outer planets would not come again until the middle of the 22nd century. If humans wanted to see Uranus and Neptune up close in the lifetimes of anyone then alive, the launch had to happen in the late 1970s. The window was narrow. Miss it, and the chance was gone for generations. At first, the dream was bigger than what we eventually built. Engineers sketched out something called the Grand Tour. 4 or 5 spacecraft packed with instruments sweeping across the outer solar system in pairs. It would have been one of the most ambitious missions ever attempted, but the cost was very high and the budgets of the early 1970s were tight. The full Grand Tour was cancelled. What survived was smaller, simpler, and in some ways more clever. 2 spacecraft originally planned only to visit Jupiter and Saturn. They were given the modest name Mariner Jupiter-Saturn. Later they would be renamed Voyager 1 and Voyager 2. The engineers, though, quietly built them stronger than the official mission required. They added shielding. They wrote flexible software. They left room for the spacecraft to keep working long after their first tasks were done. If the budget had not allowed the grand tour, perhaps the spacecraft themselves could grow into it. The design itself was unusual. Each probe carried a large dish antenna, almost 12 feet across, pointed back toward Earth. Long booms reached out from the body, holding instruments away from the warm electronics. A small generator, powered by the slow decay of plutonium, would keep them alive in the cold dark beyond the sun's warmth. Their bodies were wrapped in gold foil and quiet metal panels. They looked in some ways like strange mechanical insects, all spindly arms and silver bowls. Building them was its own quiet drama. The engineers had to imagine every problem the spacecraft might meet across a journey that would last longer than many careers. Radiation around Jupiter could fry the electronics. Dust near Saturn's rings could puncture sensitive parts. The cold of deep space could freeze fluids and crack seals. Each problem had to be solved on the ground, in advance, with no chance to send a repair crew later. There were debates about which instruments to include. Cameras, of course. Magnetic field sensors. Detectors for charged particles. Instruments to listen for radio waves from the planets themselves. Every gram added to the spacecraft meant more fuel needed at launch. Every choice was a small argument between curiosity and weight. Even the timing of the two launches required care. Voyager 2 actually launched first on the 20th of August 1977. Voyager 1 followed about 2 weeks later on the 5th of September. Voyager 1 took a faster path and would reach Jupiter first, though it left second. The names did not match the launch order, which has confused people ever since. Looking back, it is striking how close this whole effort came to never happening. If Flandreau had not noticed the planetary alignment, if the budget cuts had gone slightly deeper, if the engineers had built only to the minimum specification rather than quietly over-engineering for a journey they hoped would last. If any of these small things had broken the wrong way, the two probes would not be out there now, still whispering back to us across the dark. What remains an open question even today is how much of their long survival was careful planning and how much was simply good fortune. The engineers prepared for many things, but no one truly knew in 1977 whether these machines would still be speaking nearly 50 years later. They built them with hope, and the hope so far has held. In the spring of 1979, the first of the Voyager probes drew close to Jupiter. The view it sent back was unlike anything human eyes had seen before. The planet filled the dark with bands of cream and rust and pale gold. Storms turned slowly across its face, each one wider than our entire world. Jupiter is not a world of rock and stone. It is a giant ball of gas, mostly hydrogen and helium, the same two elements that make up most of the sun. In fact, if Jupiter had grown a little larger long ago, it might have ignited and become a small second star. Instead, it stayed a planet, but a planet made of the oldest, lightest stuff in the universe. Hydrogen and helium were born in the first minutes after the beginning of time, long before any star existed. When Voyager looked at Jupiter, it was looking at material almost as old as the cosmos itself. The colors in those famous Jupiter clouds come from heavier ingredients mixed into the gas. There is ammonia, which freezes into pale white crystals high in the sky. There are traces of sulfur and phosphorus, which paint the deeper clouds in shades of brown and orange. There is methane, water vapor, and faint hints of other compounds whose exact recipe is still being worked out. Researchers continue to debate which mix of chemicals gives the great red spot its strange salmon color. The simple answer is that we are not entirely sure. The great red spot is itself an open mystery. It is a storm wider than Earth, spinning slowly in the southern half of the planet. Voyager watched it churn, and even today no one fully understands why it has lasted so long. Some researchers wonder if it draws energy from deep inside the planet, where heat still rises from Jupiter's slow squeeze of its own weight. Others think the storm should have faded long ago, and that something we have not yet identified keeps it alive. In recent decades, it has been shrinking. Whether it will vanish in our lifetime or simply shift into a new shape remains an open question. Below the visible clouds, the gas grows thicker and warmer. Pressure builds until the hydrogen behaves in ways we cannot easily test on Earth. One idea is that far down inside Jupiter, hydrogen turns into a kind of liquid metal, flowing like mercury and carrying electric currents that generate the planet's huge magnetic field. Voyager helped confirm just how huge that field is. If we could see it with our eyes, Jupiter's magnetic shield would appear larger in our sky than the full moon. But no one has ever directly observed the metallic layer inside. It remains a theory supported by math and by hints in the data, still waiting for fuller proof. What strikes me most is how Jupiter connects to everything else. The hydrogen in its clouds is the same hydrogen that fills the sun, the same hydrogen that fused inside ancient stars, long dead, became the carbon in your burns and the oxygen in your breath. The iron at the center of Earth was forged in the heart of a star that exploded billions of years ago. The water in our oceans may have arrived, drop by drop, on the backs of comets and icy chunks falling from the outer system. Jupiter, with its enormous gravity, helped shape where those icy chunks went. It flung some inward toward the young Earth and pulled others away into deep space. In a quiet way, the gentle rain of comets that filled our seas may owe something to this giant gas world. So when Voyager turned its cameras on Jupiter and sent the pictures home, it was showing us more than a beautiful planet. It was showing us a museum of the early universe, a place where the oldest gases still swirl in patterns we do not fully understand. Every band of cloud is a recipe of elements borrowed from dying stars and from the first moments of time. Every storm is a puzzle of physics still being solved, and every measurement Voyager made raised new questions that newer probes are still trying to answer. As you settle into the quiet, picture those slow cream and rust ribbons rolling across a planet so large that 1,000 Earths could fit inside it. Picture the pale white ammonia crystals drifting in the upper sky. Picture the deep warm pressure far below, where hydrogen may flow like a strange silver river. We have visited, we have looked, we have learned a great deal, and still Jupiter keeps most of its secrets, turning slowly in the dark, waiting. When the Voyager probes drifted past the great gas giants, they did not only see the planets themselves, they saw the moons. Small worlds, frozen and strange, each one shaped by forces we are still learning to name. Some of these moons turned out to be far more alive than anyone had guessed. And the reason for that liveliness sits at the heart of an open question we have not fully answered even now. Consider Io, the innermost large moon of Jupiter. Before Voyager 1 flew past in 1979, most people imagined Io as a quiet, cratered ball of rock, much like our own moon. What the cameras returned was something else entirely. The surface glowed in oranges and yellows and pale sulfur greens. Tall plumes rose from the ground in slow arcs, rising hundreds of kilometers into space. Io was erupting. It was, and still is, the most volcanic body we have ever seen. The force behind those eruptions is something gentle to describe and violent in practice. It is called tidal heating. Jupiter is enormous, and its gravity pulls hard on Io. The other large moons, Europa and Ganymede and Callisto, also tug on Io as they pass. Caught between these pulls, Io is squeezed and stretched over and over like a rubber ball being kneaded by invisible hands. That constant flexing heats the inside of the moon. The heat melts the rock. The molten rock finds its way to the surface, and the surface, again and again, breaks open into fire. No one had predicted this before Voyager arrived. The discovery rewrote what we thought a small moon could do. It also raised a quieter question. If gravity alone could melt the inside of one little world, what else might it be melting elsewhere, in places we could not yet see? The answer began to appear at Europa, the next moon out. From a distance, Europa looked smooth, almost too smooth. As Voyager drew closer, the cameras showed a surface of bright ice, cracked through with long, dark lines that ran for thousands of kilometers. Some lines curved, some lines crossed. Some seemed to have moved and refrozen. The ice looked young. There were almost no craters, which meant something kept wiping the surface clean and starting over. One theory, still alive today, is that Europa hides an ocean of liquid water beneath its frozen shell. Tidal heating, the same gentle squeezing that lights up Io, might be warm enough on Europa to keep water liquid far below the surface. Some researchers wonder if that ocean could be deeper than any ocean on Earth. Others remain cautious. The Voyager probes could not see through the ice. They could only hint. The question of whether Europa truly holds a hidden sea and whether anything might stir within it remains open. Farther out, around Saturn, the moons grew stranger still. Voyager looked at Enceladus and noticed a surface so bright it reflected almost all the sunlight that fell on it. The reason was not yet clear. The cameras saw smooth plains, fresh ice, and very few craters in places. Some unseen process was refreshing the surface. Later missions would find geysers of water vapor venting from the south. Voyager only saw the puzzle, not the answer. It saw something that did not behave the way a small, cold moon should behave. Then there was Titan, Saturn's largest moon, wrapped in a thick orange haze that the cameras could not see through. Voyager measured the atmosphere and found mostly nitrogen, like Earth, but cold beyond imagining. What lay beneath the haze stayed hidden. Some scientists guessed at lakes of liquid methane. Others guessed at slushy ice. The probe moved on without answers. The forces shaping these moons are quiet and patient. Gravity pulls, and the pulling never stops. Radiation from Jupiter bathes the inner moons in invisible energy, slowly altering their surfaces. Magnetic fields trap charged particles in great looping currents that brush past the moons as they orbit. Over millions of years, these soft, steady pressures sculpt worlds. They crack ice. They warm hidden seas. They paint surfaces in colors that no one expected. What Voyager showed us in those brief flybys was that small worlds need not be dead. A moon does not have to be large to be active. It only needs to be squeezed in the right way by the right neighbors for long enough. Whether any of those hidden interiors hold more than warmth and water is a question we still cannot answer. The probes glimpsed enough to make us wonder. They did not stay long enough to know. And so the moons remain quietly turning. Saturn waited for them like a patient host. After Jupiter, the two probes pressed on through the long dark, each carrying a little of the giant planet's gravity tucked into their motion like a gift. The trip took years. Voyager 1 arrived first in November of 1980. Voyager 2 followed 9 months later, and what they found there changed the way we think about rings, about moons, and about the shape of choice itself. To understand the scale of Saturn, picture a beach ball sitting in a quiet field. If Saturn were that beach ball, Earth would be a single marble, set down nearly 100 paces away. Saturn is so large that more than 700 Earths could fit inside it. Yet it is so light, so puffed up with hydrogen and helium, that if you could find an ocean wide enough, Saturn would float on it. The whole planet, ring and all, would bob on the water like a great pale apple. The rings themselves are the strange part. From far away they look solid, like a smooth disk of glass. The Voyagers showed us they are not solid at all. The rings are made of countless pieces of ice and rock, some as small as grains of sand, some as large as houses, some the size of small mountains. They orbit Saturn in flat, wide bands, each piece going its own slow way, bumping and sliding past its neighbors. If you could stand on one of the larger chunks, you would see the others drifting past you in slow motion, glittering in the distant sunlight. The whole ring system is enormous in width and almost nothing in depth. The main rings stretch about 280,000 kilometers across. That is wide enough to lay 70 Earths side by side. And yet the rings are only about 10 meters thick in most places. 10 meters. The height of a tall tree. Imagine a sheet of paper the size of a city. That is something like the shape of Saturn's rings. Vast in width, almost vanishing in thickness. The Voyagers passed through this strange flat world and sent back pictures of patterns nobody had expected. Braided rings, spokes, gaps where small moons swept the ice clean. It was at Saturn that the mission split in two. Voyager 1 had a choice to make, and the choice was final. It could swing close to Titan, Saturn's largest moon, the one wrapped in thick orange haze. Or it could continue on toward Uranus and Neptune. It could not do both. The geometry of gravity does not allow second tries. The mission planners chose Titan. They wanted to know what was hidden beneath that orange veil, whether there was a surface, a sea, a sky we might recognize. Voyager 1 dove close, looked hard and learned what it could, and in doing so it bent its path upward, out of the flat plane where the planets travel, and began climbing into the unknown. That single decision is part of why we are listening to two different stories tonight. Voyager 1 left the line of the planets behind and began aiming toward open space. Voyager 2 stayed on the long road, keeping the option to visit Uranus and Neptune still alive. Two probes, one choice. Two completely different futures unfolding from that moment near Saturn. The distances involved are hard for the mind to hold. When Voyager 1 left Saturn, it was already about 1.5 billion kilometers from Earth. Light from the sun, which crosses from the sun to our planet in just 8 minutes, took more than an hour to reach the probe at that distance. A radio signal sent home took the same long hour to arrive. The engineers on Earth had to wait, send their instructions, and wait again. Every conversation became a slow exchange of patient whispers across a widening gulf. And the rings, for all their drama, are quiet. There is no sound in space. The pieces drift and tumble in silence. The Voyagers sailed past without disturbing a single grain. They took their pictures, gathered their numbers, and moved on. Behind them, the rings kept turning as they had been turning for some long stretch of time. Perhaps 100 million years, perhaps far longer. Researchers still wonder how old they really are and how long they will last before the ice falls slowly inward and disappears. One idea is that they are young and fading. Another is that they are ancient and renewing. The question remains open. Voyager 1 turned. Voyager 2 stayed the course, and the long quiet stretched out before them both. In January of 1986, after almost 9 years of quiet travel, Voyager 2 reached a world that no spacecraft had ever visited before. The planet was Uranus, a soft blue-green sphere drifting in the cold outer dark. It is hard to picture how alone the probe was in that moment. The sun, from there, looked like a very bright star, not a sun at all. Light took nearly 3 hours to reach the planet. And in that pale, distant light, Uranus waited. If you could float above its cloud tops, you would see a world unlike any other in our system. The color is the first thing you would notice. A pale, milky blue-green, almost the shade of sea glass, soft and even, with very little texture to break the smoothness. Voyager 2 looked for storms, for bands, for the kind of swirling patterns Jupiter and Saturn wear so openly. It found almost nothing. The planet looked, at first, like a polished ball of frosted glass. That stillness puzzled the team. Some researchers wondered if Uranus was simply a calmer world by nature, with weaker internal heat. Others suggested the probe had arrived during an unusually quiet season. The question of why Uranus looks so featureless is still open. Later telescopes have caught brighter clouds drifting across its face, hints that the planet is not as sleepy as it first appeared. But why it was so quiet in 1986 and what its weather is truly like underneath remains a mystery we have not been able to revisit. The atmosphere itself is mostly hydrogen and helium with a small amount of methane mixed in. That methane is what gives Uranus its color. The gas absorbs red light and lets blue and green light scatter back out. So the soft sea glass shade is not paint or rock or ocean. It is a trick of chemistry played out across a planet 4 times wider than Earth. There is something else strange about Uranus, something Voyager confirmed but did not explain. The planet lies on its side. Its axis is tipped nearly 90 degrees, so it rolls around the sun like a barrel instead of spinning like a top. One pole faces the sun for decades at a time, then the other. No other planet in our system is tilted so far. One leading idea is that long ago Uranus was struck by something enormous, an impact powerful enough to knock the whole world over. Another possibility is a slower process, perhaps a gravitational tug from a vanished moon or a long dance with the other giant planets. We do not know which story is true. We may never know. From above the cloud tops, you would also see the rings. They are not bright and broad like Saturn's. They are thin, dark and narrow, like fine pencil lines drawn around the planet. Voyager photographed them in soft, indirect light, and they appeared almost charcoal in color. Some researchers think the dark material is rich in carbon, perhaps changed by long exposure to radiation. Others wonder if the rings are young, the shattered remains of a moon that came apart not so long ago in cosmic time. The rings of Uranus hold their own quiet questions. And then there are the moons. Voyager 2 found new ones on its approach, small and pale, and it studied the larger ones with close, careful eyes. Miranda was the strangest of all. Its surface looked broken and stitched together, with cliffs taller than anything on Earth, and patchwork plains that did not match each other. One theory says Miranda was once shattered and slowly reassembled by its own gravity. Another says its insides churned in strange ways, putting fresh material to the surface in mismatched blocks. The truth is still uncertain, written in scars we have only glimpsed once. Voyager 2 did not stay. It could not stay. Its path was already bent toward Neptune, and its visit to Uranus lasted only hours of close encounter after 9 years of waiting. The probe gathered what it could, took its photographs, measured the magnetic field, and then slipped past into the dark again. Every piece of close-up knowledge we have of Uranus comes from that single brief visit nearly 4 decades ago. No spacecraft has returned. Plans have been sketched, missions proposed. But for now, the pale blue-green world spins on its side in silence, watched only from very far away. Somewhere out beyond it, Voyager 2 still drifts, carrying the memory of that quiet encounter. The first and so far only time a small machine from Earth came close enough to see Uranus with its own eyes. In August of 1989, 12 years after it left Earth, Voyager 2 reached the last planet on its long path, Neptune, a world so far from the sun that sunlight there is dim and silver, less than 1,000th as bright as the sunlight we know. From that distance, the sun is barely more than a sharp star. And yet, in that deep cold, something was moving. Voyager 2 found a planet draped in blue. Not the soft blue of Earth's oceans, but a deeper, denser blue, the colour of ink held up to a candle. The clouds drifted in long white streaks above that blue, pulled and stretched into shapes that looked almost brushed on. There was a great dark oval in the southern half of the planet, a storm the size of our entire world, swirling slowly in the cold. Voyager called it the Great Dark Spot. And when later telescopes looked, it was gone. Other dark spots have come and gone since. Why they fall, how long they last, what stirs them up from below, the question is still open. The winds at Neptune are the fastest winds ever measured on any planet. Some gusts there reach more than 1,500 kilometers per hour, faster than the speed of sound on Earth. That alone is strange. Neptune sits so far from the sun that it should be a sleepy place, with very little energy to drive its weather. The other giant planets at least bask in slightly warmer light. Neptune barely receives any at all, and still its winds scream around the planet faster than anything on Jupiter, faster than anything on Saturn. One idea is that Neptune carries its own heat from deep inside. Measurements from Voyager suggested the planet radiates more warmth than it receives from the sun. Maybe more than twice as much. Something down in the depths is glowing, releasing slow heat into the cold upper layers. That heat may be what drives the winds. But where exactly the heat comes from, and why Neptune produces more of it than its near twin Uranus, remains uncertain. Two planets that look like siblings, yet behave so differently in their hidden interiors. Below the clouds, the picture grows even stranger. Researchers think Neptune is not made of solid layers like Earth and not of simple gas like the Sun. Instead, it may be mostly a thick hot soup of water, ammonia and methane, pressed so hard by gravity that the soup behaves like nothing on our planet. Some models suggest that deep down the pressure is so extreme that carbon atoms in the methane could be squeezed into tiny diamond crystals. Those crystals, if they fall, would slowly fall through the dense fluid like a strange, sparkling rain. It is only an idea. No instrument has ever reached down there to see. There may also be an ocean of a different kind. Not water as we drink it, but a hot, electrically charged fluid that flows around a small rocky core. That flowing layer might explain Neptune's strange magnetic field, which is tilted at a sharp angle from the planet's spin and offset far from its center. Voyager 2 measured this tilt and surprised everyone. Uranus has a similar oddity. Why both planets have crooked, off-center magnetic fields is still a puzzle. Some researchers wonder if it points to a shared event in their early lives. Others think the fluid layers themselves create the tilt naturally. The evidence is incomplete. Voyager 2 also found rings around Neptune, faint and dusty, made of dark material. They are not bright like Saturn's rings. They are thin, broken in places, and seem to form clumpy arcs rather than smooth bands. How those arcs hold together over time is still being studied. Tiny moons may be shepherding the dust, gently herding it with their gravity. The full mechanism remains debated. And then there is Triton, Neptune's largest moon, which Voyager 2 photographed in the same brief visit. Triton orbits backward against the spin of its planet, which suggests it did not form there. Many researchers believe Triton was captured from somewhere else, perhaps from the icy belt of small worlds beyond Neptune. Voyager saw plumes of dark material drifting up from its frozen surface, hinting at activity beneath the ice. What drives those plumes, and whether Triton hides a hidden ocean below its crust, is still an open question. After Triton, Voyager 2 had nothing left in front of it. No more planets, no more close encounters scheduled. It turned its instruments outward toward the dark and kept going. The blue planet shrank behind it slowly until it was just one more point of light and the quiet, long part of the mission. By the time Voyager 1 had passed Saturn, finished its planetary work, and turned its slow gaze outward, it was already very far from home. The year was 1990. The little probe had been flying for 13 years. It was about 6 billion kilometers from the sun, drifting through a dark and quiet stretch of space, where the planets were now only points of light behind it. A request came up from Earth: turn the camera around, take one last look back. The idea had been suggested years before by an astronomer who loved the long view of things. He wanted Voyager to photograph the planets it had left behind, while it still had the power and the angle to do so. Mission planners worried at first. Pointing the camera back toward the sun was risky. The bright light could damage the sensors, and the planets from that distance would be almost nothing, tiny specks lost in glare. But in the end, the team agreed. The command was sent. Voyager turned and slowly, patiently took a series of photographs of its own solar system from the outside. When the images came back, one frame in particular held the attention of everyone who saw it. In a thin band of scattered sunlight against the soft grain of deep space, there sat a single pale blue speck, less than a pixel wide, almost lost. That speck was Earth. Every ocean, every mountain, every person who had ever lived, every cycle of summer and winter, every tide and every harvest, all of it gathered into that one quiet point of light. It is one of the strangest cycles in this whole story. The planet that built the probe, that listened for its signal, that turned with the seasons while Voyager pressed outward, now appeared as nothing more than a faint blue grain in a much larger darkness. The cycles of Earth, its spinning days, its leaning seasons, its long, slow wobble, became invisible at that distance. From 6 billion kilometers out, none of it moved, none of it shone. It was simply a dot. The image came to be called the pale blue dot, and it raised a question that has stayed open ever since. Not a scientific question exactly, though science is woven through it. More a question about scale, and about what our place in the universe means when seen from far enough away. Some who looked at the picture felt small. Others felt strangely held. The same speck that looked so fragile also contained everything anyone had ever known. Both feelings can be true at once, and neither one has ever quite been resolved. Cycles in the cosmos work at every scale. A moon goes around its planet in days, a planet goes around its star in years, a star goes around the center of its galaxy in hundreds of millions of years. And the galaxy itself drifts through patterns we are only beginning to understand. The Voyagers move through all of these nested rhythms, but at their own slow pace, leaving each one behind in turn. When they took the pale blue dot picture, they were already outside the cycle of the inner planets. The familiar beat of seasons no longer applied to them. They had entered a slower rhythm, one measured not in years but in centuries. Some researchers have wondered whether there are still larger cycles we cannot yet see, long sweeping motions of the sun through clouds of interstellar gas, or gentle tides from the galaxy itself, pulling on the outer edge of our solar system over millions of years. The evidence for these slow patterns is still incomplete. One possibility is that the heliosphere, the bubble of solar wind that shields the planets, grows and shrinks with these motions. Another is that the boundary stays mostly steady, breathing only a little. The Voyagers may be helping us tell the difference, simply by reporting what they feel as they move. But all of that is for later sections. For now, picture that one image again. A camera, cold and small, turning at the edge of the planetary system. A thin shaft of sunlight scattered through the lens, and inside it, a single blue mote holding all of human history, without anyone on board even knowing. The probe took the picture and then powered its camera down to save energy. It has not taken another photograph since. The image remains the last visual postcard from Voyager, a single quiet glance back at the world it came from, before it turned again and continued into the dark. The cycles it had known were ending. New, slower ones were beginning. Bolted to the side of each Voyager probe, in a quiet spot near the main body, there is a small golden disk. It is about the size of a dinner plate. It shines a soft, warm yellow, even in the cold of deep space. The disk is made of gold-plated copper. Inside its protective cover, it carries sounds, images, and greetings from Earth. The disks are called the Golden Records. There are two of them, one on each probe, and they are identical. The team that made them did not know if anyone would ever find them. They simply chose to send something, just in case. The records were never meant to be read by people. They were meant for whoever or whatever might come across the probes in the far future. Think about what that means for a moment. Two small machines were leaving our solar system forever. Someone had to decide what to put on board. What would you choose to send if you only had room for a single disk and it had to speak for every person who had ever lived? The team that worked on the records was small, and they had only a few months to finish. They picked sounds and images that felt important. They chose music from many different parts of the world. They added greetings spoken in dozens of languages. They included pictures of plants, animals, oceans, and people. They tried to show a planet that was alive, without saying too much about its troubles. There is no way to know if these choices were the right ones. Some thinkers have wondered if the records say too much. Others have wondered if they say too little. The truth is that no one really knows what a stranger from another star would notice or care about or understand. The whole project rests on a guess about minds we have never met. That guess is the heart of the mystery. The records assume that somewhere, eventually, there might be a listener. Being able to find the probe, lift it from the dark, and read what is etched on the disk. Whether such a listener exists is one of the oldest open questions in science. Some researchers think life is common across the galaxy. Others think it may be rare, perhaps even unique to Earth. The evidence is still thin on every side. If listeners do exist, we do not know how they would think. They might use senses we do not have. They might not see or hear or read in any way we would recognize. The Golden Record tries to get around this by including simple drawings, basic shapes, and patterns that follow the rules of math. Math, the team hoped, is the same everywhere. A circle is a circle on any world. 2 + 2 makes 4 no matter who counts. Yet, even this hope is just a hope. Some scholars wonder if other minds would even notice the disk as a message. They might see only a strange metal object with no meaning at all. Or they might read it in a way we never planned, finding patterns we did not put there. The record could mean one thing to its makers and something very different to its finders. We have no way to test which is true. The cover of each record carries a small map. The map shows the position of our sun in relation to 14 bright, fast-spinning stars called pulsars. The idea is that a clever finder could use the map to trace the probe back to where it came from. Some have asked if that was wise. Others say the map is so faint and the distance is so great that the worry is small. Both views are reasonable. Neither can be proven. What we can say for certain is this: the records are out there now. They are moving slowly through the dark between the stars. Each one carries the laughter of children, the sound of a kiss, the cry of a whale, the wind on a beach, a heartbeat, and a long, careful selection of music from across our world. They carry hellos in Akkadian and Welsh, in Mandarin and Quechua. They carry the shape of a hand and the curve of a leaf. Whether anyone will ever hear them is a question we cannot answer. The galaxy is wide. The probes are small. The disks may drift for 1 billion years without ever passing close to another world. Or they may, one quiet day, come to rest in a place where someone is waiting. Both endings remain possible. Both remain open, and for tonight, that openness is its own kind of company. On each of the 2 Voyager probes, fixed to the outside like a small offering, rides a disc made of copper and plated in gold. It is roughly the size of a dinner plate, 12 inches across, sealed inside a protective aluminum cover. The cover itself is etched with diagrams, and pressed into the grooves of the disc in a language older than words is sound. The records spin slowly when played, at 16 2/3 revolutions per minute, half the speed of an ordinary vinyl record. That slower turn lets them hold more. The makers wanted to fit as much of Earth as they could onto a single round surface. So they chose. They chose carefully, knowing the choice might be the only one ever made. The sounds pressed into the gold are among the most extreme objects humans have ever sent away from home. They are the farthest traveled recordings in history. They are the only known phonograph records moving through interstellar space. And barring some unlikely collision, they may also be the longest-lasting human artifacts ever created, expected to remain readable for hundreds of millions of years, possibly more than 1 billion. That last figure is worth sitting with for a moment. 1 billion years. The pyramids have stood for about 4,500 years and are already wearing away. The oldest cave paintings are roughly 40,000 years old, and they survive only because they were sealed in stone. The Voyager records, drifting in the near-perfect cold of deep space, face almost no weather, no rain, no wind, no oxygen to rust them. only the slow, soft drizzle of cosmic rays, and the occasional grain of interstellar dust. The sounds themselves were chosen to span the extremes of human and natural experience. There is the rumble of thunder, the rolling of surf against a shore, the patter of rain. There is the crackle of fire, possibly the first sound our ancestors ever truly listened to. There is the call of a humpback whale, the song of a wild dog, the chirp of crickets, the heavy footfall of an elephant. There are tools at work. There is a kiss. There is the cry of a newborn baby, and the steady beat of a human heart. There is also music, pulled from across the world, a Bulgarian folk song sung by a shepherdess, a bamboo flute from Japan, panpipes from the Solomon Islands, a wedding song from Peru, drumming from Senegal, bagpipes from Azerbaijan, a blues recording, a piece of classical music written by Bach, a short song from the Navajo Nation. The makers tried to reach across continents and centuries, knowing they could only ever offer a thin sliver. What makes this an extreme is not just the variety, but the compression, the whole noisy weight of a living planet squeezed into a little under 2 hours of audio. Every cathedral bell that ever rang, every lullaby ever hummed, every storm that ever broke over a forest, all of it reduced to a few dozen sounds standing in for the rest. The grooves that hold these sounds are unimaginably small. To read them, a future finder would need to spin the disk at the correct speed and trace its surface with something like a needle. A diagram on the cover shows how. It also shows the position of our sun, marked against a pattern of 14 pulsars, those rapidly spinning stars that flash with such regularity they work like cosmic clocks. The idea was to give any finder both a map to where we live and a calendar showing roughly when the record was made. Whether anyone will ever read it is the deepest open question of all, and we will sit with that question more as the night goes on. For now, the extreme is simply this: 2 small golden discs traveling faster than almost anything humans have ever made are right now carrying the sound of a baby crying past stars whose light has not yet reached Earth. Some who worked on the records have said they think of them as a kind of message in a bottle, more meaningful for the act of sending than for the chance of arrival. Others have wondered whether they will be the only trace of us left, long after the Earth itself has changed beyond recognition. Both possibilities remain open. Neither can be confirmed. What is certain is that somewhere in the cold dark, 2 flat golden circles are spinning gently in place as their carriers drift onward. They hold a thunderstorm, they hold a heartbeat, they hold a kiss, and they are quietly, slowly becoming the most enduring sound recordings our species has ever made. Tucked into the golden records, beside the music and the sounds of our world, there is something gentler still. A small chorus of voices speaking in many tongues. Short greetings, each one only a sentence, or too long, recorded by people who came to a studio at Cornell University in the spring of 1977. They spoke into a microphone, and their words were pressed into the gold along with the rest. There are 55 of these greetings, 55 different languages gathered in a quiet hurry, each one a tiny doorway into a culture. Some of the languages are spoken by hundreds of millions of people. Some are spoken by only a few thousand. A few are very old, with roots that reach back thousands of years. They sit side by side on the record, equal in length, equal in weight, traveling now in the same silence. The greetings are simple: a hello, a wish for peace, a note of welcome to whoever or whatever might be listening. In one language, a voice says, in effect, "May all beings everywhere be happy." In another, the speaker offers greetings from the children of planet Earth. In another still, the voice simply says hello and asks how you are. The small politeness of that question, carried into the dark between stars, is a thing worth pausing over. No one knows if any of these words will ever be heard. That is part of their quiet beauty. They were recorded not for an audience that exists, but for one that might. The people who spoke them were not famous. They were students, professors, neighbors who happened to know a language the project needed. They walked into a small room, said a few warm words, and walked back out. Now their voices drift past the Heliopause, carried by two small spacecraft that no longer have any way to hear a reply. Some of the recordings include things you would not expect. A few speakers added small touches of their own. One greeting wishes the listener good health. Another says in a tone of friendly hope that we are trying to make our world a better place. The shortest greetings last only a second or two. The longest stretch to perhaps 10. Together, all 55 take only a few minutes of the record's long, quiet running time. The record also carries a greeting from a whale. The sound was placed in among the human voices, a low and looping call from one of the great singing animals of our oceans. Scientists who chose the contents thought it only right. If the record was meant to greet other minds, then perhaps the other minds of Earth deserved a place too. The whale's voice travels now beside the human ones, with no translation, no introduction, just the long sound of a creature singing in the dark. There are other small details on the record that few people ever notice. A short message in Morse code, tapped out in slow dots and dashes, spells out a Latin phrase often translated as "through hardships to the stars." It sits quietly among the pictures and sounds, easy to miss unless you know to look. A pulse of code, an old human habit of sending meaning through patterns, carried now into a place no telegraph wire could ever reach. And there is laughter, a single recording of human laughter, brief and unguarded, was included among the sounds of Earth. No one knows whose laugh it is exactly. Some accounts suggest it belonged to one of the people working on the project. It plays for only a moment, a small bright sound, the kind of sound a person might make in a kitchen, or while reading something funny, or while looking up at the stars and feeling for a moment glad to be alive. What any of this means to a listener who is not human is an open question. Some researchers wonder if the patterns of speech would be recognizable as speech at all, without a shared body and a shared world to anchor them. Others think the music and the natural sounds might travel further across the gap of understanding than the words. There is no way to test these guesses. The record speaks, and we cannot hear how it sounds on the other side of that great silence. For tonight, it is enough to picture the gold disc turning gently in the dark, with 55 small voices pressed into its grooves. A whale singing, a pulse of old code, a single human laugh, all of it moving outward at a steady, patient pace, into a quiet that has no edges we have ever found. Long before the Voyager probes ever left Earth, people wondered where the sun's influence ended. The sun gives us light and warmth, but it also gives off something else. It breathes out a steady stream of charged particles in every direction. This stream is called the solar wind. It flows past the planets like a slow river of glowing gas, too thin to see with our eyes. For most of human history, no one knew this wind existed. The ancient astronomers watched the sun rise and set. They mapped its path across the sky. They tracked its spots when telescopes finally let them. But they had no way to feel the wind that poured from its surface. The space between worlds looked to them like simple emptiness. The first hints came slowly. In the early 1900s, a few thoughtful observers noticed that comet tails always pointed away from the sun. It did not matter which way the comet was moving. The tail always streamed outward, as if some unseen breath were pushing it. A German astronomer named Ludwig Biermann wrote about this in the 1950s. He suggested that something must be flowing out from the sun, fast and constant, strong enough to bend the tails of comets. A young American physicist named Eugene Parker took that idea further. In 1958, he worked out the math of a hot, expanding outer atmosphere around the sun. His equations showed a wind that should fill the whole solar system. Many older scientists doubted him. The paper was nearly rejected. The idea seemed too strange, too bold. Yet within a few years, the first spacecraft to fly far from Earth carried instruments that detected exactly what he had predicted. The solar wind was real. Once we knew the sun had a wind, a deeper question opened. Where does it stop? The wind cannot blow forever. Somewhere out in the dark, the sun's breath must thin, weaken, and meet the breath of other stars. Beyond the planets, beyond the comets, there had to be a kind of shore, a boundary where our star's reach finally ended. Scientists began to imagine this boundary as a great bubble. They called it the heliosphere, meaning the sphere of the sun. Inside the bubble, the sun's wind sets the rules. Outside, the wind of the galaxy takes over. The shape of the bubble is not a perfect ball. As the sun moves through the galaxy, the bubble gets pushed into a long, soft teardrop, blunt on one side and trailing behind on the other. Or so the early models suggested. The exact shape is still debated today. No one had ever measured this edge. No one had ever crossed it. For decades, all we had were estimates, sketches on paper, and educated guesses. Some thought the boundary lay around 50 times the distance from the Earth to the sun. Others thought it might be 100 times that, or more. The truth depended on how strong the solar wind was, how dense the gas between the stars was, and how the two pushed against each other. Each new measurement shifted the answer. When the Voyager probes were launched in 1977, no one expected them to reach this boundary. Their main job was to study the giant planets. They were not designed to be edge finders. But after they finished their planetary visits, they kept moving outward, faster than anything humans had built before. Slowly, year by year, it became clear that they might one day touch the shore. The instruments aboard each probe were simple by today's standards. They could count charged particles. They could feel changes in the magnetic field. They could measure the direction and energy of the wind around them. As the Voyagers traveled deeper into the dark, those numbers began to change in small, telling ways. The solar wind grew slower. It grew thinner. It began to swirl in ways the engineers had never seen before. Researchers on the ground watched the data come in, sometimes weeks at a time, sometimes month by month. They were watching, in the most literal sense, the slow fading of our sun's voice. No human had ever charted such a region. No theory was complete. Each new reading raised as many questions as it answered. This is how the discovery has unfolded, not in a single moment, not with a triumphant announcement, but with two small machines drifting outward, sending back numbers that slowly redrew the map. The edge of the sun's reach was no longer a thought experiment. It was becoming a measurement, a real place, a place we were finally, for the first time, beginning to touch. For most of their long flight, the two probes moved through a thin wind of charged particles streaming out from the sun. This wind has a name. It is called the solar wind, and it is made of bits of hot gas blown outward in every direction. The wind pushes against the cold gas of the space between the stars. Where these two meet, they form a kind of bubble. Scientists call this bubble the heliosphere. It is the sun's own little weather system, surrounding all the planets like a soft, invisible balloon. The outer skin of that balloon has a name too. It is called the Heliopause. This is the boundary where the sun's wind finally loses its strength, and the gas of deep space pushes back. No one had ever crossed it before. No one knew exactly what it would feel like, or what the instruments would see. For decades, people argued about where the edge truly was. Some thought it would be a sharp wall. Others thought it would be soft and fuzzy, blurred over millions of miles. In August of 2012, Voyager 1 crossed it. The crossing surprised almost everyone who studied it. For one thing, the boundary was not a slow fade. It was sudden. Over the course of about a day, the count of solar wind particles dropped to nearly nothing. At the same moment, the count of cosmic rays from outside the solar system jumped sharply upward. Cosmic rays are tiny, fast-moving bits of matter thrown out by exploding stars, far away in the galaxy. Inside the bubble, the sun shields us from many of them. Outside, they pour in freely. What surprised researchers even more was the magnetic field. Many had expected it to change direction at the boundary, to swing around and match the magnetic field of the wider galaxy. It did not. The field outside still pointed in roughly the same way it had pointed inside, and this was strange. It did not match what most of the models had predicted. Some scientists wondered if Voyager had really crossed the Heliopause at all. Others thought the boundary might be more layered, more tangled than anyone had guessed. The question is still not fully settled. Voyager 2 reached the same edge 6 years later, in 2018, on a different path through the bubble. Its crossing also looked sudden, but the details did not perfectly match its sibling. The two probes recorded slightly different conditions at the boundary, even though they were both, in some sense, leaving the same room. This puzzled people. It suggested the heliopause is not a smooth shell, but a wrinkled, shifting surface, pushed and pulled by the wind of the sun and the wind of the stars beyond. There were smaller surprises too. Just before Voyager 1 crossed, it entered a quiet zone where the solar wind seemed to almost stop moving outward. The particles still danced, but they no longer streamed. Some researchers called this region the stagnation layer. No one had predicted it. It was as if the wind had reached the end of a long hallway and was milling about, unsure where to go next. And then there is the matter of how thick the boundary really is. From far away, on paper, the heliopause sounds like a line. In truth, it may be a thick, foamy region full of bubbles and ripples where the sun's gas mixes slowly with the gas of the galaxy. The probes only sampled tiny threads of it as they passed through. The full shape remains a mystery. Some maps suggest the bubble is round, like a ball. Other maps suggest it is stretched out behind us, like a soft comet tail. We do not yet know which picture is closer to the truth. What we do know is that two small machines, built in the 1970s, became the first human-made objects to taste the space between the stars. They did not find a wall. They did not find an empty void. They found a quiet, complicated edge, more layered and more surprising than anyone had drawn on a chalkboard. They are still drifting outward, sending back slow whispers about what that region is really like. Each new whisper adjusts the picture a little. Each one raises a few new questions. So the surprise of the heliopause is not just that the probes crossed it. The surprise is that the crossing did not match the textbook. It rewrote the textbook gently in pencil, leaving margins wide enough for the next discovery to fit. And out in that thin, layered boundary, the two travelers continue their slow drift, listening to a sea no one fully understands. There is a question that sounds simple, but quietly opens into something much larger. When does a spacecraft truly leave the solar system? The Voyagers have crossed one boundary, the heliopause, where the sun's wind gives way to the wind between the stars. Yet many scientists would say the two probes are still inside the solar system and may remain so for tens of thousands of years. The reason has to do with how the sun's influence reaches outward. Light and solar wind are only part of the story. Gravity stretches much farther. Holding on to distant bodies, the sun has never warmed in any meaningful way. Far past Neptune, far past Pluto, there is thought to be a vast shell of icy worlds called the Oort cloud. It may begin a few thousand times farther from the sun than Earth is, and reach outward perhaps 100,000 times that distance. The Voyagers have not entered it yet. By that measure, they have only stepped into the doorway, so the solar system has at least two edges, and they do not match. There is the edge of the sun's breath, which the probes have crossed, and there is the edge of the sun's pull, which lies far beyond. The space between those two edges is strange and quiet. Inside it, the solar wind no longer reaches, but the sun's gravity still does. The Voyagers drift in this in-between zone, neither fully home nor fully away. This is where the topic begins to connect with everything else. The sun is not a single thing acting alone. It is a layered presence, with one influence ending where another keeps going. Its light fades with distance, but never quite stops. Its magnetic field bends and tangles with the fields of other stars. Its gravity blends very gently into the gravity of the galaxy itself. The solar system does not have a sharp wall. It has a slow fade. The same is true closer to home. The sun touches the ocean by warming its surface, lifting water into clouds, and driving the winds that push the waves. Volcanoes touch the climate by sending ash and gas high into the air, dimming sunlight for a season or two. One galaxy can tug on another across distances so vast that the pull takes hundreds of millions of years to be felt. Nothing in the universe seems to end at a clean line. Everything leaks into everything else. The Voyagers are small messengers inside this larger pattern. They were built to study planets, but they have become probes of these soft layered edges. By measuring how the particles around them change, they show us where one region of space gives way to the next. They are how we learned that the Heliopause exists in the way it does, and how we began to understand that it is not a wall but a kind of shoreline with tides and ripples of its own. There is an open question here that researchers still sit with. If the sun's gravity holds objects out to the Oort cloud, then the Voyagers, moving at their current speed, would need roughly 300 centuries to reach its inner edge, and far longer to pass through it. By then, their signal will have ended long ago. We will never receive data from inside the cloud, so the question of when the probes truly leave the sun's domain may never be answered by the probes themselves. It will have to be answered by theory, by inference, by missions we have not yet built. Some scientists prefer to mark the boundary at the Heliopause, because that is where the sun's particles end. Others argue that the gravitational boundary is the more honest one, because it is the sun that holds the system together. Still others say there are several boundaries, each meaningful in its own way, and that asking for a single edge misses the point. The solar system, they suggest, is better understood as a set of nested zones, each one fading into the next. The Voyagers connect all of these ideas in a single, slow gesture. They began inside the warm inner planets, passed through the cold outer worlds, slipped beyond the wind of the sun, and are now drifting through the long region where only gravity still speaks. Each step has taught us that the universe layers itself in soft folds rather than hard walls. The sun reaches into the dark reaches back, and somewhere within that overlap, two small machines keep moving, still part of the sun's family, still listening, still carrying the faintest hum of home into a space that has no clear name. Think of a whisper, a real whisper spoken across a quiet room. Now imagine that whisper traveling for nearly a full day before it reaches your ear. That is, in a soft and patient way, what is happening every time the Voyager probes send a signal home. The light from their tiny radio transmitters takes more than 20 hours in each direction to cross the gulf between them and us. And the strength of that signal, by the time it touches our antennas, is almost too small to imagine. Voyager 1 transmits with about 22 watts of power. That is roughly the same as a small refrigerator bulb. By the time those radio waves spread across more than 15 billion miles of empty space, their strength has faded to something close to a billionth of a watt. We catch them anyway. We catch them because we know exactly where to listen, and because the dish antennas we use are enormous, and because the math of how to pull a whisper out of pure noise has been refined for over half a century. The change here is slow and quiet, but it never stops. Every day the probes drift a little farther. Every day the signal grows a little weaker. Every day the team on Earth listens just a bit more carefully. The conversation between us and these two small machines has not gone silent. It has simply become more and more delicate, like trying to hear a single voice in a vast and gentle wind. When the probes launched in 1977, sending data home was easy. Voyager 1 was still within the inner solar system, and its radio signal arrived strong and clear, full of pictures and measurements. The early years were loud, in a sense. The probes shouted, and we listened without effort. Then the distance grew. Jupiter passed. Saturn passed. The outer planets fell behind. With each year, the same 22 watts had to stretch across a larger and larger sphere of space, and the signal at our end grew thinner. This is just geometry. Radio waves spread outward in all directions, like ripples on a pond, and their strength falls off with the square of the distance. Double the distance, and the signal becomes 4 times weaker. The probes are now more than 100 times farther from us than they were at Saturn. The arithmetic is humbling, and yet we still hear them. The way we hear them has changed too. The dishes of the deep space network, scattered across Earth in California, Spain and Australia, have grown larger and more sensitive over the years. Receivers have been upgraded, signal processing has improved. Engineers have learned, slowly, how to coax meaning out of fainter and fainter traces. In some ways, our ears have grown sharper, at the same rate the probes have grown quieter. There is also a slow change in what the probes themselves can say. As power fades, instruments must be switched off one by one to keep the most important ones alive. The conversations grow shorter, the bandwidth narrows. Where once full streams of colour pictures crossed the void, now only thin trickles of numbers remain, describing the magnetic fields and charged particles of the space around each craft. The richness of the early years has given way to a quieter, simpler kind of message. There is something tender about that if you sit with it. 2 small machines, built decades ago, are still trying. They send what they can. They keep their radios pointed, more or less, in our direction. And we, on a small planet they may never see again, keep our great dishes turned toward where we believe they are, listening for a whisper that grows fainter by the year. No one knows exactly how long this will continue. The power source on each probe is a slow heat engine, fueled by the decay of plutonium, and it weakens a little each year. Eventually, there will not be enough warmth to run even a single instrument. Eventually, there will not be enough power to lift the radio above the noise. Whether that moment comes in the late 2020s or the 2030s, or somewhere in between, remains an open question. Engineers extend the lifetime in small, clever ways, but the trend is steady. For now, the change is gentle. Every night, the antennas turn. Every night, the signal arrives, perhaps a little softer than the night before. The conversation has not ended. It has only grown more careful, more patient, more like listening for a friend's breathing in a darkened room. The whisper still returns. We are still here in the quiet, choosing to hear it. To hear a whisper from beyond the solar system, you need a very large ear. The signals from the Voyager probes arrive at Earth so faint, so spread out, so worn down by the long crossing, that no ordinary antenna could pick them out from the hiss of the universe. By the time the radio waves reach us, they carry less power than the glow of a single distant star reflected in still water. To catch them, NASA built something extraordinary, and it watches the sky in 3 places at once. The system is called the Deep Space Network. It is made of 3 sites spread around the planet, roughly a third of the world apart from each other. One sits in the high desert of California in a place called Goldstone, where the dishes rise from sand and pale stone. Another stands near Madrid in Spain, surrounded by rolling hills, the colour of straw in summer. The third rests in Canberra in Australia, ringed by gum trees and dry grass. Together, these 3 sites form a kind of triangle around the Earth. As the planet turns, at least one of them is always facing the right part of the sky. The largest dishes at each site are massive white bowls, 70 meters across. That is wider than a soccer field. They sit on huge mounts that let them tilt and turn with quiet, careful grace. From below, they look like cathedrals turned to face the stars. When the wind moves through their open frames, they hum softly, the way a seashell hums when you hold it to your ear. They are some of the most sensitive listening devices our species has ever built. The light they listen for is not visible light, it is radio light, a much longer, slower kind of wave. Radio is part of the same family as the light that lets us see colours and warmth, but its waves stretch out across centimetres instead of fractions of a hair. The Voyagers send their signals in a thin band of these waves, chosen long ago because they pass cleanly through the dust and gas between the stars. Visible light scatters and bends. Radio light at the right frequency slips through the dark like a thread pulled through silk. When a Voyager signal finally arrives, it has been travelling for more than 20 hours. It has crossed empty space, colder than almost anywhere a human has ever touched. It has passed through the faint plasma of the interstellar medium, the thin soup of charged particles drifting between the stars. By the time it brushes the great dish in California or Spain or Australia, its power is measured in tiny fractions of a billionth of a watt. The antenna gathers this whisper, focuses it, and feeds it into receivers chilled almost to absolute zero so that no warmth of their own can drown the message out. There is something tender about the whole arrangement. 2 small craft, each lighter than a family car, send their patient little tones across the dark. And on Earth, 3 quiet white bowls tilt and turn day and night, listening. The dishes do not glow, they do not flash. They simply wait with the steady attention of something that has been told to listen and never to look away. Light, in its broadest sense, is how the Voyagers and Earth still speak. Sunlight reflects off the gold of the records on their hulls. Starlight falls on the lonely shapes of the probes as they drift. And the radio light they send back is the only thread of connection we still have. When the signal arrives at Canberra, the dish there catches a faint shimmer that began its journey when the craft was already further from the sun than any object ever made by human hands. It is worth sitting with the strangeness of this. The same physics that lets you see the colour of the sky also lets a giant dish in the Australian countryside hear a machine that left Earth before many listeners were born. Light is the medium of every part of the story. The blue of Neptune, the orange of Io, the gold of the record, the dim red of a dying transmitter. All of it is light in one form or another, carrying meaning across distances too large to truly picture. How long the antennas will keep hearing anything is one of the open questions that drift quietly behind this whole adventure. The probes grow weaker each year. The dishes grow more sensitive when they can. Somewhere in the middle, the last conversation will happen, and no one yet knows exactly when. For now, the bowls turn, and the sky speaks very softly in a language only the patient can hear. Inside each Voyager probe, there beats a small, quiet heart. It is not a heart of muscle, but of metal. A canister filled with plutonium, slowly warm, slowly cooling, turning its own decay into electricity. Engineers call it a radioisotope thermoelectric generator. The name is long, but the idea is simple. Heat on one side, cold on the other, and from that small difference comes power. Enough power, once, to light a few household bulbs. Not much, but enough to whisper across the stars. When the probes left Earth in the summer of 1977, each generator produced around 470 watts. That is roughly what a bright kitchen light might pull from the wall. From that small budget, the spacecraft had to run its computers, its heaters, its cameras, its radio. Every watt was counted, every watt was spent with care. Plutonium does not last forever, though. It fades, slowly, steadily, atom by atom. Each year the generators give a little less. Roughly 4 watts vanish with every trip around the sun. The decline is gentle, but it never pauses. It never reverses. The heart cools, one quiet beat at a time. After more than 4 decades in the dark, the probes now run on something like half of what they started with. 200 and something watts, give or take, depending on the year you measure. Less than the bulb in a reading lamp. From this faint glow of energy, 2 travelers still speak to Earth. If you could somehow listen to the generators themselves, you would hear nothing. They have no moving parts, no hum, no whir, no click, just the silent decay of unstable atoms, releasing heat the way coals release warmth in a banked fire. Quiet, patient, slowly running out. The probes do make other sounds, in a way. Their instruments measure the faint shiver of charged particles flowing past them in interstellar space. Plasma, it is called, a thin soup of electrons and ions left over from stars long gone. When researchers convert those measurements into audio, they sound like distant wind, a low rolling hiss, sometimes rising into a soft whistle. The song of the medium between the stars, recorded by ears made of metal and code. There is a famous recording captured by one of the probes after it crossed into interstellar space. It sounds almost like breath, a gentle moan, neither living nor mechanical, that rises and falls as the spacecraft drifts through changing currents of plasma. No one had ever heard such a sound before. No human instrument had ever been far enough to listen. And here was this small machine holding out a tiny antenna in the dark, picking up the hum of the galaxy. To keep that listening going, engineers must make hard choices. As power fades, Something must be turned off. A heater, perhaps. An instrument. A camera that has not been used in many years. Each decision is a small farewell. Each part that goes dark will not come back. The probes are becoming simpler, slowly, like an old house in which fewer rooms are lit each winter. The cameras, in fact, were shut down decades ago. There was nothing left to photograph in the darkness between stars, and the warmth they needed could be better spent elsewhere. The instruments that remain are the ones that taste the plasma, sense the magnetic field, count the cosmic rays, the senses best suited to a place with nothing to see. One open question is how long this slow fading can continue. Some engineers think the probes may keep speaking in some form into the 2030s. Others suspect even that hope may be generous. The generators will not stop suddenly. They will only become too weak to power the radio. At some point, the signal will simply fall below what our antennas can hear. Whether that moment comes in 5 years or 10 or 15, no one can say for certain. The math gives a range. The probes themselves will decide. There is something tender in this slow goodbye. A machine built by people who are no longer young, sending faint reports across an ocean of vacuum, while its own quiet heart cools. No drama, no alarms, just the steady, gentle thinning of power, like the last embers of a fire that warmed a long evening. For now the heart still beats, plutonium still decays, heat still flows, electricity still trickles through old circuits, and somewhere, eventually, it becomes a whisper aimed at Earth. We do not know how many of those whispers are left. We only know that tonight the small heart is still warm. Each Voyager carried 11 scientific instruments when it left Earth. 11 small tools, each designed to measure a different piece of the sky. Cameras for visible light, detectors for charged particles, magnetometers reaching out on long booms to feel the shape of magnetic fields, spectrometers that could split light into its colors and read the chemistry inside. It was a tiny floating laboratory, no bigger than a small car, packed with the careful arithmetic of human curiosity. Most of those instruments have been turned off now. The math of survival is simple and unforgiving. The power source on each probe drops by about 4 watts every year. To keep the probes alive, engineers must subtract. One instrument, then another. Each shutdown buys a little more time for the rest. It is a slow, deliberate trade written out on paper years in advance, like a long, quiet game of arithmetic against the cold. On Voyager 1, only a handful of instruments still gather data. The magnetometer still listens for the faint pull of magnetic fields out there in the space between stars. The plasma wave system still catches the soft hum of charged particles vibrating in the dark. The cosmic ray detector still counts the high-energy bits of matter that come streaming in from distant supernovae. Voyager 2 carries a similar small set, awake and patient, sending back numbers that no other machine in history has ever measured. The mathematics of their motion is just as elegant. Each probe moves at roughly 17 kilometers per second relative to the Sun. That works out to about 38,000 miles every hour. At that pace, they cover the distance between the Earth and the Moon in about 6 hours. They cover the distance the sun's light travels in 1 second, every single second they fly. And yet the distances ahead of them are so large that those speeds feel almost still. A light year is the distance light travels in 1 year, moving at nearly 300,000 kilometers every second. The nearest star to our sun sits about 4.25 light years away. The Voyagers, fast as they are, would need around 70,000 years to cover that gap if they were even pointed in that direction. They are not. They are aimed at empty sky. There is a quiet beauty in how predictable their paths are. Gravity follows clean, simple rules first written down centuries ago. Once a probe leaves the strong pull of the planets behind, its course can be calculated to astonishing precision. Engineers can say, decades from now, where each Voyager will be down to a small handful of kilometers. The universe, at this scale, runs on arithmetic that fits on a single page. The signal itself is governed by another piece of elegant math. Radio waves spread out as they travel, weakening with the square of the distance. Double the distance, and the signal becomes 4 times fainter. Triple it, and the signal becomes 9 times fainter. By the time Voyager 1's whisper reaches Earth, it carries less power than a refrigerator light bulb shining from across the galaxy. The receiving antennas on the ground must gather that whisper from a sky full of louder noise. There are open questions hidden inside these neat numbers. No one knows exactly how long each remaining instrument will keep working. The power drop is steady, but the instruments themselves are aging in ways that are harder to predict. A small electronic part might fail tomorrow. A heater might give out and let a delicate sensor freeze. Engineers make their best guesses, but the probes have already lasted far longer than anyone first expected. The arithmetic of their lifespan is more like a soft cloud than a sharp line. Even the data they send is shaped by careful counting. Each bit travels at a slow trickle now, only a few dozen bits per second. A single image, if they were still taking images, would take many hours to send, so the engineers choose very carefully what to ask for. Every byte is precious. Every measurement is weighed against the cost of the power it takes to send it home. There is something almost moving about that math. 2 small machines far past any planet, gently humming with the last of their warmth, choosing which questions to keep asking. The numbers are not cold at all when you look at them this way. They are the language of patience. They are the way we measure something rare. A project that has outlived its own first generation of scientists and still quietly returns answers from places we have only just begun to wonder about. How much longer the instruments will stay awake remains an open question, one that the slow subtraction of watts will eventually answer for us. The signals coming back from the Voyagers are faint beyond imagining. By the time they reach Earth, the power in those radio waves is so small that it borders on the unmeasurable. And yet somewhere in California, in Australia, in Spain, dish antennas catch them. Engineers read them. People still listen. What is strange, and what often goes unsaid, is that the people listening today are not the same people who built the probes. The engineers who first wrote the code that runs aboard Voyager 1 and Voyager 2 are mostly retired. Some have passed away. The hands that soldered the boards, the minds that drafted the original software, are no longer in the room. So a small team at the Jet Propulsion Laboratory now speaks to a machine through a language that was in many ways written for a different century. The computers aboard the Voyagers run on memory measured in kilobytes. The instructions were composed in assembly code and in a programming language called Fortran, both of which are rarely taught to young engineers anymore. To work on Voyager today is to learn a kind of forgotten tongue. The team keeps thick binders, paper binders, with notes scribbled in the margins decades ago. When something unexpected happens on the spacecraft, they sometimes have to go searching through old documents, hunting for a comment left by an engineer who is no longer alive, hoping that comment explains why a certain switch behaves the way it does. It is a quiet kind of archaeology, done not in dust and ruins, but in code and memory dumps. Think about how delicate this balance is. The probes were built to last 5 years. They have now been working for nearly 50. Every command sent up must travel for over 20 hours just to arrive. The answer takes another 20 hours to return. A simple back and forth conversation, the kind a person might have in a single breath, takes nearly 2 full days between Earth and Voyager 1. If a wrong command is sent, there is no way to call it back. The radio wave is already on its journey, racing through the dark at the speed of light, indifferent and unstoppable. Engineers test every instruction over and over before it leaves the ground. A single mistake could end the mission, and there would be no one to fix it. In recent years, the team had to face a strange problem on Voyager 1. The spacecraft began sending back garbled data. Numbers that should have made sense came home as noise. After months of careful study, the engineers traced the trouble to a single chip in the onboard memory. One small piece of hardware, drifting in the cold for half a century, had finally started to fail. They could not replace it. They could not even touch it. Instead, they wrote new code that worked around the broken chip, slicing the affected software into smaller pieces and tucking those pieces into other parts of the spacecraft's memory. It was a kind of digital surgery performed from billions of miles away, using tools written before most of the surgeons were born. And against the odds, it worked. The data came back clean. Still, the mystery of how long this can continue is wide open. Every year, more components age. The radioactive power source grows weaker. Heaters that keep the fuel lines from freezing have already been turned off one by one to save energy. The probes are slowly going dark from the inside, like a house where the lights are switched off room by room as winter deepens. One theory is that careful management could keep at least one instrument alive into the 2030s. Another view is more cautious, suggesting that an unexpected failure could end communication at any moment. Both could be true. No one really knows. The Voyagers were never designed for this. They are working past every promise that was made about them. There is something tender in the picture of it. A handful of engineers in a quiet building, speaking softly to 2 old machines through a language almost no one else remembers, pressing buttons that ripple outward across the solar system, waiting nearly a full day to hear if the machines reply. It works because countless small things still work. The chip that has not yet failed. The antenna still pointed more or less at home. The thin trickle of warmth from a slowly fading source of heat. Any one of these could falter, none of them so far have given up entirely. And so the conversation continues, a whisper from the dark, answered by a whisper from the desert. Two old voices still speaking, while the people who taught them to speak quietly listen and wonder how long the words will last. So we come to the part of the story where the map runs out. We know, in a general sense, where the two Voyagers are. We can point our antennas at the right patch of sky and find their faint whispers waiting. We can calculate their speed, their direction, their distance from the sun in numbers that grow a little larger each second. And yet, when we ask exactly where they are drifting now, the answer becomes softer, less certain, more like a guess written in pencil. Voyager 1 is moving outward in one direction, climbing above the plane where the planets orbit. Voyager 2 is moving in another, dipping below that plane, taking a slightly different path through the dark. Both are now in what scientists call interstellar space, the thin sea of gas and dust between the stars. But this sea is not empty, and it is not still. It has currents we are only beginning to map. One open question is the exact shape of the bubble they have left behind. The sun blows a kind of wind, a stream of charged particles that carves out a vast region around our solar system. The edge of that region is called the Heliopause. For a long time, scientists pictured it as roughly round, like a balloon. Then newer measurements hinted that it might be shaped more like a long teardrop, with a tail trailing behind. Some researchers now wonder if it looks more like a crescent, or even something stranger. The two Voyagers crossed this edge in different places and at different times, and what they sent back does not quite agree. The shape of our own cosmic home is still being argued over in quiet papers and long meetings. There is also the question of what lies just outside that boundary. The space between stars is not perfectly smooth. It has thicker patches and thinner patches, warmer pockets and colder ones. Our sun appears to be passing through a region sometimes called the local interstellar cloud, a wisp of slightly denser gas. No one is entirely sure how large this cloud is, how long the sun has been inside it, or when it might drift out. The Voyagers are now taking samples from this region, but they can only sample the small patch they pass through. Everything beyond their narrow path remains a guess. Then there is the matter of the magnetic field. Out there, beyond the sun's reach, the galaxy itself has a faint magnetic field, woven through the gas between stars. Scientists expected the direction of this field to change sharply once the Voyagers crossed into interstellar space. Instead, the field on the other side seemed oddly aligned with the field inside the bubble. Why those two fields should match so closely is not understood. One idea is that the sun's field bends and presses against the galactic field, dragging it into line near the edge. Another idea is that the boundary is more porous than we thought, with the two fields mixing across a wide fuzzy zone. The measurements are not yet enough to choose between these pictures. The cosmic rays add another layer of mystery. These are tiny, fast particles that come from distant supernovas and other violent events across the galaxy. Inside the sun's bubble, fewer of them reach us. Outside, the count goes up. The Voyagers have watched this rise in detail, and the numbers do not quite match the simple models. Something is shaping the flow of these particles in ways that are still being puzzled out. Each new reading nudges the theories, but no single theory has settled the matter. And there is the simplest mystery of all, the one that is almost easy to forget. We do not really know what the space around the Voyagers looks like. We have no nearby picture of it. We have only the tiny stream of data from instruments built half a century ago, drifting through a region no human eye has ever seen. Everything we say about that place is built from those whispers. The rest is imagination, careful and informed, but imagination all the same. So when we ask where the Voyagers are drifting now, the honest answer is through a region we are still learning the rules of. They are our slow, patient scouts in a place we cannot yet describe with confidence. They are mapping a country whose borders, weather, and shape we are still arguing about. And in that uncertainty there is something gentle to hold on to, the quiet thought that even the edges of our own neighborhood remain a mystery, still waiting in the soft dark to be understood a little better. Try for a moment to picture the two probes not as they are now, but as they will be in a long, slow future. Their signals will be gone. Their power will have faded to nothing. Their instruments will sit silent inside their gold-wrapped bodies. And still they will keep moving. That is the strange and quiet truth of these two machines. Once their voices end, their travels do not. They simply drift, carried by the speed they gathered long ago. In 1,000 years, both probes will still be in the same general direction we last sent them. They will be far past the Heliopause, the bubble of the sun's wind, but only a small step into the wider sea of stars. The cold around them will be deeper than anything we can feel. No sunlight warms their panels. No planet pulls them in. They glide through empty space at about 17 kilometers each second, which is fast by any human measure, and slow beyond belief when compared to the distance between stars. In 40,000 years, Voyager 1 will pass within a few light years of a faint red star called Gliese 445. Voyager 2 will drift near another quiet star named Ross 248. Neither probe will arrive, neither will be captured by gravity. They will simply pass in the wide darkness like two ships in a fog who never see each other. By then the Earth they left will have changed. Ice ages will have come and gone. Coastlines will have shifted. The languages spoken on their golden records may no longer be spoken at all. In 1,000,000 years, the probes will still be intact. Space is a gentle museum. There is no rain, no rust, no wind, no weather. The gold plates on their sides may be slowly scratched by tiny grains of dust, but most of their bodies will remain much as they were the day they left. The aluminum will still hold its shape. The wires will still wind through their frames. The records will still carry their grooves, even if no one is left to play them. In 100 million years, the sun itself will have changed. It will be slightly hotter, slightly brighter. The continents on Earth will have rearranged themselves into new patterns we cannot quite predict. Whole mountain ranges will have risen and worn down, and still the two probes will drift. They will likely have traveled only a small fraction of the way across our galaxy. The Milky Way is wide, and even great speeds become small inside it. In 1 billion years, the sun will be warmer still. Some researchers think Earth's oceans may begin to boil away by then, though the timing is not certain. the planet may become a hot, dry world, more like Venus than the blue marble Voyager 1 once photographed. The pale blue dot will no longer be pale or blue. By that time, the probes may have completed a slow loop around the center of the galaxy, carried by the same gentle gravity that holds all the stars in their wide turning. Further still, in 5 billion years or so, the sun will swell into a red giant. It will grow large enough to swallow Mercury and Venus, and perhaps the Earth as well. The inner solar system will be unrecognizable, but the probes will not be there. They will be far away, drifting in another part of the galaxy entirely, untouched by their old home's slow death. In a strange way, they may outlive the very planet that made them. And after that, what then? The galaxy will keep turning. Stars will be born from clouds of gas. Other stars will burn out and collapse. The Milky Way itself will likely merge with the Andromeda galaxy, forming something new, a wider swirl of stars and dust. Through all of this, 2 small machines may keep their slow path, carrying their gold and their grooves, their fading metal and their patient shape. How long they last, no one truly knows. Some estimates suggest their structures could survive for billions of years if nothing strikes them. Others note that even rare collisions with dust over enough time may wear them down. The question of their final end is open. They may be ground to fragments. They may be swept into a star. They may simply keep going in some form, almost forever. For tonight, it is enough to picture them out there, quiet and steady, moving through a future none of us will see. 2 small travelers made by hands long gone, still patient in the dark. Step back now, as far as the mind can reach, and try to see the whole picture at once. 2 small machines, built by hands on a single blue planet, drifting through the dark between stars. Behind them, the warm yellow point of our sun grows smaller every year. Ahead of them, an ocean of space so wide that even light takes years to cross the smallest part of it. Think of where the atoms in those probes came from. The aluminum in their frames, the gold on their records, the copper in their wires. None of it was made on Earth. All of it was forged inside ancient stars that lived and died long before our sun was born. When a giant star collapses and explodes, it scatters heavy elements into the dark. Those elements drift for ages, gather into new clouds, and eventually form planets and engineers and spacecraft. So, in a quiet way, the Voyagers are stardust returning to the stars. The same atoms that once burned inside a supernova are now flying outward again, carrying songs and greetings from the small world where they briefly came together. The calcium in the bones of the people who built the probes came from the same kind of explosions. We and the spacecraft share that ancient story. We are simply 2 shapes the same dust has taken for a little while. This is part of what makes the question of who might find them so strange and so beautiful. The Voyagers are not really leaving the universe. They are moving from one part of it to another through a medium made of the same stuff they are made of. If they are ever found, the finders will likely be made of star material too. Every thinking thing in the cosmos, if there are others, must come from the same furnace of dying suns. Some researchers wonder whether life is common in the galaxy. Others suspect it is very rare. The honest answer is that we do not know. We have searched only a tiny patch of sky for only a few decades. The silence we have heard so far may mean there is no one listening, or it may mean we have not yet learned how to listen properly. The question remains open, and the Voyagers carry that question with them. Even if no one ever finds the probes, their meaning does not vanish. They are a record that on at least one small world, atoms once arranged themselves into beings who looked up and wondered. Beings who took copper and gold and silicon and used them to ask the dark a polite question. That gesture exists now. It is woven into the history of the galaxy, whether anyone reads it or not. Picture the long view of time. The sun will keep shining for roughly another 5 billion years before it swells and changes. The Earth as we know it will not last that long. Continents will move, oceans will rise and fall, and the species that built the Voyagers will likely look very different or be gone. Yet the probes will still be out there, moving through the slow rivers of stars, carrying the voices of people who lived in a moment now long past. In a sense, the Voyagers are messages from the dead to the unborn, written in metal. Whoever might one day intercept them, if anyone ever does, will be reading a letter from a civilization that may not exist anymore. That thought is not sad. It is simply the shape of deep time. Everything that lives gets a turn to leave a mark. The Voyagers are our mark. And the mystery at the heart of it all is not really about the probes. It is about us and about whatever else might be out there, and about the long, quiet conversation the universe seems to be having with itself. Stars are born, stars die, atoms scatter, atoms gather, and somewhere in that endless mixing, things begin to wonder. The wondering is brief. The wondering is precious. The wondering is, as far as we can tell, the rarest thing the cosmos makes. So as the night deepens around you, let the picture settle. 2 small spacecraft made of stardust, moving through more stardust, carrying the sound of a heartbeat from a planet of stardust people. No one knows who will find them, or when, or whether anyone ever will. No one knows what other quiet listeners might be drifting somewhere in the dark, doing the same thing on their own scale. The answer is out of reach for now. The question itself is enough to hold. We share atoms with the stars, and we have sent 2 of those stars back home. And so we come to the quiet end of our long visit with these 2 small travelers. The facts have been laid out gently, one after another, like stones placed along a path. The wonders have been shared. What remains is only the stillness and the soft thought of 2 machines drifting through the dark, doing what they have done for nearly 50 years. Picture them now, if you like, not as machines of metal and wire, but as small bright points moving slowly through a deep and patient ocean of space. Around them, no sound, no wind, no weather. Only the faint hum of cosmic rays, the steady push of starlight, and the long, slow turning of the galaxy itself. They do not hurry, they have nowhere to be, they simply move, and as they move, they whisper. The whisper is small. By the time it reaches Earth, it is fainter than the heartbeat of a single atom. And yet we hear it. Quiet dishes on a quiet planet tip their faces toward the sky and gather that thin voice from across the void. We listen, and the travelers speak. And for a few hours each week, the conversation continues. The signal in the dark, a thread of light invisible to the eye, stretched across more miles than the mind can hold. Below those dishes, the earth turns as it always has. Oceans rest under the moon. Forests breathe slowly in the night. Cities glow softly, then dim, then glow again, as the planet rolls into morning somewhere else. The travelers know none of this. They have not seen the Earth in many years. To them, our world is one pale blue point among many, and even that point has long since faded from view. But the Earth remembers them. Somewhere, an engineer checks a screen and sees a familiar pattern. Somewhere, a child looks up at the stars and learns their names for the first time. Somewhere, a quiet room hums with old equipment that still knows how to listen. The travelers are far away, but they are not forgotten. They never have been. And around them, the galaxy turns. It turns so slowly that no eye could ever see it move. A full turn takes hundreds of millions of years. Stars are born inside grey clouds of dust, and stars die in soft glowing shells, and between them the dark is full of patient motion. The travellers drift through this turning two tiny silver shapes among uncounted suns. They are small, they are gentle, they are exactly where they are meant to be. Maybe one day the signal will fade for the last time. The power will drop too low. The final instrument will fall silent. The conversation will end, not in alarm, but in a kind of quiet completion. And even then, the travellers will keep going. They will keep their slow course outward, carrying their golden records and their old greetings, moving among stars that will not see them pass. We may never know who finds them. We may never know if anyone does. The mystery remains open, as so many mysteries do, and that is a soft and beautiful thing to hold as you fall asleep. Not every question needs an answer tonight. Some questions are better as questions, sitting quietly with us in the dark, asking nothing in return. So let your thoughts slow. Let the travellers drift on without you. They do not need watching. They have been moving for almost half a century, and they will keep moving for billions of years, and the galaxy will hold them gently the whole way. The dark is not empty. The dark is full of patient, turning things, and we are part of that turning too. You are small, and the universe is vast, and that is a kind of comfort. You are held in your quiet room on a quiet planet, under a sky that has been there long before us, and will be there long after. Somewhere far beyond the last planet, two old machines are whispering home. The whisper is faint and steady, and full of the long story of a curious species that once looked up and decided to send something out. Sleep now. The travellers are still going. The signal is still arriving. The galaxy is still turning. Slowly, like a great wheel in the dark. Tomorrow, there will be more to wonder about. Tonight, it is enough to rest and to know that the quiet machines are quiet still, doing what they have always done, somewhere out beyond the edge of everything we know. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.